Okay, so hello again. We are still in neural networks, and we are going to talk more about how to design a neural network, how to configure it. Now, you might ask yourself, why do I have to learn this? I'm not likely to ever program a neural network or design one. And the answer is that if you want to understand how particular technologies affect society, you have to first understand how they work. You wouldn't say you want to talk about how cars affect lives in cities if you don't understand, at least on a basic level, what a car is and what it is doing. It is important, for example, that a car consumes fuel, that the fumes that come out of the car are poisonous to some extent, that the car goes at a particular speed, and you need to understand how much the speed is. So if an alien just came down to Earth and looked at cars and tried to evaluate what the relationship of cars is to society, it would be difficult for him to do that, right? If he doesn't have experience of cars. We need to know that people are lazy, they don't like to walk, but then we also need to know that shops, for example, in cities need people to walk in. And all these things, you need to understand how society works in order to be able to judge what a car is doing to society. So in the same way, here we need to understand roughly, not in detail. You don't need to know, with a car example, how the engine looks inside, although you need to understand the difference between an electrical car and a car that runs on gas. This is an important difference, right? An electric car would have totally different effects on society. Some of those will be different, some will be similar, right? But in order to understand which are which, we need to understand what an electric car, what makes it different from a gas-driven car. In the same way, when you talk about AI technologies, you need to understand what's the difference between a neural network and, let's say, Prolog or Psych. Not having this background will make it impossible for you to judge how society is affected by neural networks or by psych or by expert systems, right? So the worst thing are people who think that they're experts at something, although they have no idea of how things work, because these people are likely to come to all sorts of totally wrong conclusions and then to derive totally wrong recommendations from these wrong conclusions and make problems bigger instead of solving them. So if we want to help society, right, because we are in principle the people who are supposed to know about such things. You are the students who will go on perhaps to become AI expert at some point, or legal experts, or politicians, or decision makers in any other capacity. So you need to understand what are these technologies and how do they work at a basic level so that you can later evaluate what the dangers are and what the advantages are. So this is why we still have to go a little more into the technical detail about neural networks. It will not take long, but it will be very insightful. It will explain to you why these things work as they work and why they fail as they fail, because they also fail. And their failures are much more interesting than their successes, and much more dangerous. And so you have to be able to understand how they work in order to understand how and why they fail. Now, the design considerations when I create an artificial neural network, what do I have to think about? So first, you remember creating a neural network, an artificial neural network, ANN, in principle involves 3 stages. First, I have to configure the thing. So I have to start saying I want to create a neural network to solve a problem. And now, what do I do first? I think how many inputs, how many output neurons I need, how many hidden layers I need, how to connect all these things with each other, right? And this is the configuration of it. After I have configured it, I have my input data, my output data. Now I have to train it. After I have trained it for a while, I have to use it in my application. I have to publish it. I have to, put it out there for the users to use in some form. And then I'm in the application phase. And these are 3 different phases, and I need to understand that these are different. The programmer, for example, or the trainer of the neural network has only an effect in the training stage but he does not later control the application stage. So if the neural network, for example, learns during the application stage, then if it keeps learning, then I have a responsibility problem, right? Because I cannot say that the programmer is responsible for what the neural network has learned in the application stage, because the programmer is gone by then, right? Okay, so let's look a little more closely at this thing. So the configuration, as we said, involves first deciding about my number of layers, how many input, how many output neurons I have, how many hidden layers I have, how many neurons do they have, and the semantics of input and output. So I need to say, what does each input neuron encode? To what input is it connected? And for the output neurons, again, I need to define what does the firing of an output neuron signify in my application. What does it mean if neuron 32 fires? Does it mean, the letter A, if my neural network is producing text, or the letter A has been recognized if it is reading handwritten input, or does it mean you should accelerate your car, or does it mean you should use the brake? So I need to know what the individual neurons of the output mean as a function. What does this output mean? Because the neural network itself is just neurons that are connected, right? There is no meaning there. The meaning is supplied by the way I interpret the output, or by the way I connect it to particular motor neurons, to particular effectors that produce a change in the world. So for the handwriting recognition, as an example, I would say I have an input. My grid, you remember I had this grid in which I write letters, and then each pixel of the grid is an input to my neuron, right? So that the neuron can recognize my squiggles which I write on the paper. So I need perhaps an input of black and white pixels on an 8x8 grid. So normally this would be a little small, right? 8x8 is not so much. If you want to recognize handwriting, perhaps it would be more like, I don't know, 20x10 or 20x12 or something like this. Also, normally it wouldn't be square, because our letters tend to be higher than they are wide, right? We have all sorts of lines sticking up and down the letters, which makes them longer in the vertical dimension. So we should generally have some kind of grid. It doesn't matter now for the example, how the grid exactly is made. So let's say we have an 8x8 grid with 64 inputs. Then we need an output. What is the output of our neural network? The output is supposed to recognize handwriting. So it should tell us what letter was recognized. So I will need one neuron for each recognized letter. And when this fires, I know that this letter has been recognized, right? So this is one out of 26 will always fire, I assume, or this is what I want to have as a result. And so I need 26 outputs, one for each letter. Obviously now this is only an example. You can see why is this not good with 26 outputs. Can you try to think for a moment? Why is this not so good for this purpose? Yeah, obviously, because this would only recognize letters, but it would, for example, not tell us if they are capital letters or small letters, right? If I need to distinguish capital and small letters, I would need another 26 outputs. It wouldn't recognize punctuation or spaces or anything like that. Then I would need a few more characters. And it wouldn't recognize digits, right? We also have 10 digits, which are normally part of what we write when we write something, or when we recognize text. Digits are always, even on this page, right? If you look here, we have 8, 6, 4, 2, 6. So these are all digits that need to be recognized. So therefore, in reality, if this was for real, you wouldn't have only 26 outputs. You would have perhaps, again, 64, where you can encode all the letters, and you can encode some punctuation and some digits and so on. Okay, so that's it. And now if I have another example, car control, for example, right? What would be my input? My input would be my video image, a grid, again, it's always good for inputs to be grids, because a point in the grid maps naturally to one neuron in your input layer, right? And so making grids of things, a representation as a grid, gives you a two-dimensional view of things, which is the way our eyes also work, right? We have a two-dimensional, mostly two-dimensional vision. We can have some idea of depth through the fact that our eyes are at a distance from each other and we perceive things in 3 dimensions. But if you take a video image, this is normally good enough for most purposes to be two-dimensional. And so you would say, I have a video image of a camera that drives my car, and this might be a 100 by 100 grid, which would mean I have 10,000 input neurons in my input layer. Again, this is very small, right? If you think 100 by 100 pixels, if you make this on your computer, take a picture and get a 100 by 100 picture from the internet, or scale one of yours down with a graphics program, then you will see that almost all detail is lost. It's almost unrecognizable already. And if this was a real car with a 100 by 100 grid, it would not be able to read traffic signs, for example, right? It would perhaps just see other cars, but it would not be able to, and perhaps pedestrians, but it would not be able to recognize small animals on the street, dogs, cats. It would not be able to read traffic signs. So this would not be good, again, for the practice, right? If you want a practical video feed to actually drive a car, you would use something much bigger, perhaps 1,000 by 1,000. But you see where the problem is. If I have more inputs, what is the problem? Think of it for a moment. Why would I not, freely say, okay, let's take 10,000 by 10,000 grid? Yeah, obviously the problem is that this is more and more data, right? Because it's 2 dimensions, I have to multiply. 100 by 100 is 10,000. 1,000 by 1,000 is already 1,000,000. And each pixel now is a neuron, and each neuron needs to be simulated on my computer. So my processor on my computer needs to go and simulate each single neuron and calculate its value. And it makes a huge difference if I have 10,000 inputs or 1,000,000 inputs, right? A 1,000,000 neurons layer is much harder to calculate, right, in terms of the time I need to calculate it. And also I don't have only one layer, because I have the input layer, but then I need a few hidden layers, and then I need an output layer. And with every layer I have more and more neurons. If I have 1,000,000 neurons in my input layer, I cannot have 100 neurons in my hidden layer, because then I will lose all the information that I had in the input layer. So if I want to preserve part of this information, I need to have the hidden layer be in some good proportion to the input layer, right? It doesn't need to be exactly the same. It can be smaller, or but it has to be in some sensible proportion to it. And so I would then multiply again every time, because every connection of the input layer, you remember, if it's fully connected, then every neuron on the input layer is connected with all neurons of the hidden layer, and every neuron of the hidden layer is connected to every neuron of the next hidden layer. This means that, again, I'm multiplying. If I have 10 neurons in one layer and 10 neurons in the other layer, I don't have 10 connections, I have 100 connections, because every one connects to every other. So my synapses, which is what I'm calculating, are 100. If I have a 100 by 100 grid, I have 10,000 inputs. If I have 2 layers, I have 10,000 by 10,000 synapses in there. And if I have another layer, then I have to multiply again with 10,000. So you see that these numbers explode very quickly, right? It's an exponential growth. So the more neurons I add, the more these numbers explode. And this is the reason why people always try to keep it as small as possible, right? And against an exponential explosion, not even fast computers help very much. Of course, it's better to have a fast one than a slow one. But if you keep multiplying numbers with themselves, this exponential growth, right, this curve will grow much faster than the abilities of your hardware. So you can kill every hardware by making these huge neural networks that are then impossible to calculate. So you should therefore always try to be conservative with the number of neurons, right? This is another thing. Okay, and you have more inputs, right? For a car, you have distance sensors, radar, other sensors. All these things need to be taken into account. Now, what would be the output of a neural network for car driving? Think about this for a moment. Yeah, obviously, right, it would be the neurons that connect directly to the effectors, to the motors that control the car. So you would have outputs like 1 neuron for turn right, 1 neuron for turn left, 1 neuron press the accelerator, 1 neuron for the brake. You would have 4 outputs. If the car can go backwards, perhaps you can have a fifth for the back, going back. And this is why this neural network, you see, would be very asymmetric. You would have huge number of inputs, you would have very few outputs, and in between you have reducing numbers of neurons in your hidden layers so that you can in the end map all these inputs to the small number of your outputs. Okay, so this is how you would configure this thing, and we have multiple examples, so I don't want to show you all these things now, but here's an example of in YouTube of a self-driving, simulated self-driving car that is driven by a neural network, and you can get some idea of how this would look like. Okay, now when I'm training a neural network, I also have to consider that when I train the neural network with particular patterns, you remember what I do is to put an input pattern and an output pattern, and to tell the neural network to remember the correlation, right? To learn the correlation between the input and the output, so that when this input is applied, I get this output. This is the supervised learning, right? I give it input and expected output, and its job is to minimize the output error. Now, if I have only, let's say, 100 inputs that I have in my training set with which I train the network and 100 corresponding outputs, then after I finish training, I wouldn't be able to test it if it has learned very well and if it can generalize. For a discussion of a generalization, go back to the previous lesson. Because the neuron will have already learned all the patterns that I have. I have only 100 patterns, let's say. I have trained the 100 patterns. Now the neural network has seen all my 100 patterns and learned on them. So now how do I test if it has really learned to categorize correctly new patterns? And I would need some new patterns. So in order to make this easier, I normally would separate my original data into a training set. Let's say 80% of my data I use for training, and a validation set. 20% of my data I would use for validation, and the 20% for validation I would not use for training, so that I have data with which to test my network, which the network has never seen before. And this is useful because then I can judge if the network actually works with new data, if it can generalize to new data, or if it has just memorized my input data, which would not be so good, right? So this is why we separate our original bunch of data that we have for training into one training set that we actually train with, and one validation set that the network does not train with, but that we can use to validate, to show, to prove that it has actually learned correctly. And yeah, this is all explained here. And in this way we can test if the neural network can actually recognize new patterns that it has never seen before. So now you have to also remember that the neural network doesn't want to memorize everything, right? When I say this is very important again to understand. It's a part of this generalization thing, right? We talked about already. So I want to have a neural network to recognize my face, right? And now I train with pictures of my face, but if I train only with pictures of my face with my glasses on, then the neural network will learn that my glasses are part of my face. So taking off my glasses now will not produce a correct identification of my face, because the neural network thinks that this is now a different face. It lacks the glasses. So I need to somehow make sure that the network understands that my glasses are not part of what makes my face my face. So this is why I distinguish between features of something, which are the properties of the data set that the network should actually learn to recognize, that are relevant, and noise, which is not what the network should learn to recognize. So in this picture, if you look at your screen now at my little picture here, right, this has lots of noise that the network should not recognize. What is noise? All the background behind me is noise. The network should not learn that these papers are part of my face. The network should not learn that my glasses are part of my face. The network should not learn that a particular kind of hairdo is part of my face, or the color of my t-shirt. It shouldn't recognize me only if I'm wearing my black t-shirt. It should recognize me only with the red, also with a red t-shirt, right? So this is why these are not features. So the features of the input data is what you really want to be part of the recognition. My eyebrows, my eyes, the shape of my nose, the shape of my mouth, you know, the width and height of my head and so on. These are things that are used to actually recognize me and distinguish me from other humans. Whether behind me is a wall of papers or not is not part of what makes me. If behind me were trees, it would still be me. So this is noise. All right? So a network for face recognition should learn to identify features like the eyes, the nose, and the mouth of the person, but it should not memorize shadows in a particular picture. If the light falls from there or from there, this doesn't make a difference for the face. We also don't want it to memorize particular makeup or temporary features of a face like a pimple, right? Or let's say I hit my nose and now my nose is red, so this you shouldn't memorize that. So, but it's important to see that these are still part of the input data. So my input data contain all these noisy elements, but these are not the features we're interested in. So where the features are what I really want the network to learn. And so as the network learns and minimizes the output error, it converges towards the desired output. The error over time goes down as the network converges toward the desired behavior, right? You remember this? If not, go back to the previous session. So if something is wrong now with the network architecture, for example, if the network does not have enough neurons or not enough hidden layers, then the network will not successfully converge. I want the network to minimize the output error. You remember in the beginning, the weights are random, so the error is big. It does not recognize anything. But as I train it, I want it to change the weights so that the error is minimized, it gets less and less. And in the end, it will learn that for this output pattern, it produces that output pattern. For the input pattern, it produces that output pattern. And it will learn to do this with a minimum of error. But now let's assume that I have only 5 neurons and I try to learn, to recognize a face. Then obviously the 5 neurons don't have enough synapses. They don't have enough moving parts. They don't have enough permutations of state to be able to remember different faces. There's just not enough processing capacity in there, right? If I want the network to recognize features of my face, I need, to recognize the nose. The nose is a particular shape. It needs a few dozen neurons to be able to outline the shape of the nose and the eyes and so on. If I have only 5 neurons, then you can imagine, like painting a face with 5 pixels. It's not possible. It's not enough information, right? You can try to paint a face with 5 pixels, but it will not look like a face, and one face would not look different from another. So if I want to distinguish between different faces and distinguish a face from a statue or perhaps from a football, then I need to have more than 5 neurons, right? So the network will never converge if it doesn't have enough neurons. So although you keep training the network, the error stops getting smaller at some point and stays constant because the network is not able to remember all the information you want. And therefore you need to either simplify the input or make the network bigger, or try a different way of arranging things inside the network, right? Not all networks need to be fully connected, for example. Some networks can be connected only some neurons to other neurons. And sometimes, depending on how your data is, this might be advantageous. So obviously, the more hidden neurons your network has, the more synapses it has, and therefore the capacity to learn will be higher, right? Because all the stored information is in the synapses, right? It's all in the synapses. And so the more synapses you have, the more moving parts the thing has, and the more information can be stored. The more pictures, let's say, your neural network can distinguish, because it can remember more details. So the capacity to learn of a neural network is directly proportional to the number of its synapses. And this means to the number of layers, or to the number of neurons per layer. So then, bigger networks can learn more things. They can distinguish better, they can distinguish clearer between data, and they can learn more different data. So if this is true, that bigger networks perform better, then why don't we only use very large numbers of neurons and layers? Can you think about this for a second and try to answer this question? Well, the bigger the network, the longer it takes to train. And this relationship is exponential, like we said before, right? Every neuron of one layer is connected to every neuron of the next layer. Then in one layer of 10 neurons, you have 10 synapses. If you have a second layer, you have 100 synapses. If you have a third layer, which is the same size, you will have 10,000 synapses. So the more layers you add, and you never have 10 neurons, right? You normally have like 100 or 1,000. And so now you can see how this explodes. This is why we try to keep as few neurons as possible, but this also must be as many as necessary. So you want to keep them as small as possible for the speed of the learning and processing, but you want to have as many as you can, because this gives you more capacity of the neuron to actually learn things, of the neural network to learn things. So now another problem which I would have, if I had many neurons, let's say I have a very fast computer which doesn't have a problem with calculating millions of neurons, what I will then get a problem is called overfitting. And overfitting is interesting because the synapses in the neural network essentially try to memorize their input patterns. Well, this is what they do. But they cannot memorize all the input. Because if the neural network has too few synapses, then it will not be able to distinguish between all the relevant features of the input. It will not converge. The input error will not go towards zero. On the other hand, if it has too many synapses, then it will be able to memorize every single feature of the input, and not only the features that I want, but every single element of the input, and it will not generalize. So if I had a neural network with thousands of neurons or millions of neurons and pointed now to this video picture, it will not only memorize my face, but also my glasses and also my hair and also my beard and also the background. And then it will not easily learn to generalize. Now you say, okay, then show it a picture of myself without the background. But if it has enough synapses, then it would also learn the backgrounds. It would just memorize the different backgrounds. And then it would again not generalize. So the point is, you want the network to be able to memorize my face, but you don't want it to be able to memorize the shadows cast by the light or the makeup on the face or the glasses. If you make the network big enough, it will try to memorize everything that it can. So keeping the network small forces it to learn the distinction between desirable features of the input and noise. A network that is too big just memorizes everything, and then it has not learned to generalize, right? It's only when the network is unable to memorize accidental noise, because it does not have enough synapses to do that, that it is forced to learn the difference between relevant features and accidental noise. Otherwise, it never learns that, and then it is a bad neural network. So it does this learning how to distinguish by encoding the relevant features that appear again and again, while one-time noise is not encoded and therefore later not recognized by the network. So this is the reason now why, when you design a neural network, you don't want to make it either too big or too small for the task at hand. Too big, it will memorize everything and not generalize. Too small, it will not be able to memorize the important features, and then it will not converge. Finding just the right dimensions for a neural network is an art. There is no automatic solution to tell you how to configure it. This is why this is a skill that you get from working a lot with neural networks, and this is why AI experts are so well paid, because they know how to do this, right? If you do this right, the network will optimize learning time, accuracy, and the ability to generalize all at the same time. If you do it wrong, you end up either with a network that doesn't generalize or with a network that doesn't distinguish all the features. So there are some rules of thumb about this, but researchers get better at this only through long experience and by trying out different parameters and seeing what works best. Okay, so that's it. These are some of the considerations that you have to keep in mind when you design a neural network, or that now you know others keep in mind when they do this, even if you never do it. Again, this is important to understand, because then you understand what the problem is when a self-driving car, for example, does not generalize correctly, or when a self-driving car, the neural network is too small and it cannot memorize the important features of the input. So you need to understand what the problems are and what the trade-offs are in order to be able to judge how neural networks affect society. Okay, next we will talk about examples of neural networks. We'll see some examples and how they work. So come back for the next lesson in a moment. Thank you.